Chitosan is a fascinating material in the field of sustainable materials science because it bridges green chemistry, circular economy, and advanced functional materials. Here's an overview of current research directions and applications. Source and sustainability. Origin. Chitosan is derived from chitin, the second most abundant natural polymer after cellulose, found in crustacean shells, shrimp, crab, lobster, insect exoskeletons, and fungal cell walls. Sustainability. It valorizes seafood waste streams into high-value biomaterials, aligning with waste-to-resource and circular bioeconomy strategies. Biodegradability. Chitosan is biodegradable, renewable, and non-toxic, making it ideal for replacing petroleum-derived polymers. Research in sustainable materials. Feedstocks, extraction, and green processing. Chitosan's footprint is dominated by how we get chitin from shells and how we deacetylate it. Conventional sodium hydroxide, hydrochloric acid workflows are effective, but waste and energy-intensive. Deep eutectic solvents, DES, and ionic liquids. Multiple 2024 to 2025 reviews and case studies show DES, for example, choline chloride-based, can delaminate, deproteinize insect crustacean shells at lower temperatures and be recycled, improving E factors versus mineral acids/alkali. Fungal/insect chitin is especially DES amenable and avoids seafood allergens. Mechanochemistry. Solvent-free ball milling routes can cross-link or functionalize chitosan, e.g. with polyanions, and directly yield robust sorbents, useful for water treatment without wet chemistry. Packaging films and coatings. Chitosan is a leading biopolymer for antimicrobial or oxygen barrier films. Recent reviews cover chitosan/PVA blends, metal oxide nanocomposites, and anthocyanin/flavonoid systems that provide both antimicrobial activity and freshness-indicating color change. Case study, 2025. IIT Hyderabad reported a nanocomposite film from sewage sludge EPS plus Chitosan plus calcium oxide nanoparticles, eggshell-derived. Even though it's not for food contact, it hits circular economy marks and improves tensile strength, elongation, and water barrier. Muscle-inspired barrier/adhesive layers. Catechol/tannic acid chemistry, grafted onto chitosan, improves wet adhesion and enables antimicrobial coatings for food preservation. Water treatment and environmental remediation. Heavy metals, dyes, pharmaceuticals, PFAS. Literature review confirm chitosan's dominance among bioadsorbents, selectivity and capacity scale with grafted chelators/cross-link density, PFAS specifically. Two strategies show promise. Cross-linked chitosan networks improve PFOS uptake while resisting swelling/leaching. Hybrid sorbents, covalent organic framework particles anchored on chitosan, markedly boost PFAS capture via hydrophobic/ionic sites. Bioadhesives, hydrogels, and functional coatings. Muscle-inspired chitosan hydrogels. Dopamine/catechol-modified chitosan yields fast gelling, strong, wet adhesive networks for tissue sealing and wound care. Recent reviews map chemistry and clinical leaning performance, toughness, self-healing, antibacterial. For sustainable materials, these same chemistries translate to wet bonding coatings for paper/bioplastics and anti-fouling layers, replacing petroepoxies in some uses. Energy and electronics toward biodegradable components. Proton exchange membranes, PEM. Sulfonated, phosphorylated chitosan, often with nanofillers or ionic liquids, is emerging as a bio-based alternative to Nephyon for low-temperature fuel cells. Recent 2024 to 2025 reviews report conductivity gains and better high-humidity performance, while durability, oxidative stability remain the gating factors. Battery binders. Chitosan is a water-processable, mechanically dissipative binder for silicon and silicon graphite anodes. Challenges and research opportunities. Scalability. Industrial-scale extraction and deacetylation processes need greener, more efficient methods. Property limitations. Pure chitosan has poor water stability and mechanical strength. Thus, blending or cross-linking is essential. Functionalization. Need for green chemical modification routes to tailor hydrophobicity, conductivity, or thermal stability. Standardization. Variability in molecular weight and degree of deacetylation affects reproducibility and performance. Future outlook. Circular bioeconomy, using waste seafood shells as feedstock for high-value biopolymers. Green composites, replacing petroleum-based plastics in packaging, coatings, adhesives, and textiles. Smart, sustainable materials. Development of biodegradable electronics, sensors, and actuators from chitosan. Regenerative medicine. Biopolymer scaffolds with controlled degradation for sustainable health care. Non-food circularity wins. The IIT Hyderabad sludge eggshell case shows how far non-food packaging can push circular inputs. Expect municipal and agricultural waste pairings with chitosan matrices.